Let me actually bring it up. So I guess today we are going to discuss the sample questions, right? So let's see how we can move on with that. All right, Miss Fatima Begum again. She is late, so no more joining meeting. Share. Let me know if you can see my screen. Okay. So I have two sets of questions. Guess each set has 18 questions. I don't remember the other one. Let me check again. Yeah. So 18 and 18, 36. The total 36. I guess I'm going to skip one of the question about, uh, what was that? Let me see. How did I arrange this? Okay. If you recall in our previous discussion or the summary for the midterm lectures, I had that serial number SL001 and so on. So those serial number will correspond to these questions also. Like the very first one, the question is, by using Ohm's law, prove the increase of resistance will cause the current to decrease. Okay. So let me go back and just to show you how we can relate those two. So this was our serial number one, and the question was, by changing the resistance, we can change the current, just like this. So serial number one will include this column and column on the left and on column on the center at the center. Okay, this is how you will be able to relate. Okay, let's see. And by the way, no recording though. If I find out anyone is recording, um, there will be consequences for that. Okay. I think the idea was that you are going to go through these problems, and if you have any question, I'm going to answer those questions. So, does anyone has any question? I'm going to go by the attendance. AB Siddiq Tawhid, do you have any question? Let's move on to the next one. Abun Ahmad, do you have any question?
No, sir.
Uh, did you say no?
Yes, sir. No, sir. I don't have any question.
Okay, so okay, all right. Abhishek Dotto, do you have
No,
any
sir.
question?
No, sir.
Antara Raida Hawk, do you have any question?
No, sir.
All right. Asif Arman Nail.
No, sir.
All right. Ekram Ahmed Ryan.
No, sir.
All right. So HM Shahira.
No, sir, I don't have any question.
Okay. Ikram Patwari.
No, sir. No question.
Zarin Tarannum Anan.
Sir, would it be possible to discuss question 7?
Sure. So let's see. Question 7. What are the major predictions of Schrödinger equations? I don't remember which lecture that was. The major prediction for Schrödinger equation is that the electrons will occupy different energy bands. In a potential well, the electron will occupy different potential bands. That is the major prediction. Or I guess it's also in the summary lectures. And also the tunneling effect. Okay. So I think the answer is given here. So this is serial number 7, and you asked for the question number 7. So this is the prediction that there will be a barrier, a tunneling through the barrier. Okay.
Sir, thank you, sir.
And also there will be band structure. The carrier will stay in a band. Or any other question? Who was that?
Sir, it was
Uh,
me, Zarin
okay.
Taranumanan.
Okay. Any other question?
Sir, question 32.
32. Okay. Okay. So here we have question number 32. Answer the following. Derive the Einstein's equation for diffusion coefficient and mobility. And it would be from lecture number 4, I guess. Maybe 4B. So this should be, I don't know what the slide number here is, I guess slide number 14 from 4A. What we do, we have the expression for electric field is given by this equation. And we know electric field is equal to voltage divided by length. Other and also energy is given by charge times voltage. So we can relate uh, the energy band with the electric field through voltage. So here electric field is proportional to the the derivative or the gradient of energy band. Energy band. If we replace the energy band in this equation, we relate the electric field with the voltage. And as I mentioned earlier, the electric field will be equal to dV by dx, voltage divided by length. Now, if you do the math in this equation, then it should be you should be able to derive this formula where we have diffusion coefficient divided by mobility is equal to kT by q, and this expression is called Einstein's equation or Einstein's relation.
So thank you, sir.
All right. Any other question from Zarin Taranum Anand?
No, sir. Thank you, sir.
Okay. Let's go to the next one. Junaid Rafid, do you have any question? Well, let me check that particular question. 25. So it should be here. Okay. So you don't need VCD. Do you need VCD? You have current though. I don't remember the equation, but okay, no, I don't think that. Let me check anyway. So, okay, lecture 4. I don't know. Oh, do you remember which lecture? Oh, I think that was from 3. 3. Okay. This one? Okay, let me check. VCD divided by R. So, resistance. VCD equal to resistance. This resistance comes from if a measurement of resistance R is given. Okay, so here if you go through this statement that we need to calculate the we need to measure the resistance first. Okay? So if we know the resistance, then we should be able to calculate the VCD from it. Does it make sense? What was what was the question? Let me go back. I don't remember the question. So Ix is equal to this, and V equal to this. Carrier concentration, resistivity. So we need to know the resistance. That's true. And if you know the resistance, okay. Uh, Thank you for pointing this out. I'm going to revise this equation or the question and assume a resistance. Or if you want to do it right now, just assume a resistance. Suppose resistance equal to one ohm. Okay. So uh, so I'm going to I'm going to revise it. So let me take a note of it. Okay. What is next one? And the question is, what is your question? Confusion. But I understand. What is wrong here? Is there anything wrong or uh, I'm yes, yes. Mm, yes, yes. What is the variation of EF between material 1 and material 2 in the figure? So this is the figure. Here we have I equal to 0. So when the current is equal to 0, we call it equilibrium condition. And for the equilibrium condition, uh, the particle that the particle move from left to right must be equal to particle moving from right to left. As a result, that means uh, that's the only way we can make this current zero at equilibrium. And if we do the math, that was I don't remember exactly, maybe two, right? Okay, two, 3b, 3b, right? So this right. So if we calculate the number of particle from 1 to 2, also calculate the number of particles from 2 to 1 and make it equal, because they must be equal and opposite because our current is 0. If we make it equal and do the derivation, then we will see the Fermi level on the left hand side is equal to Fermi level on the right hand side. That means the derivation, the change of Fermi level is 0, or the gradient of Fermi level is 0. Yes, so that question is correspond to that particular slide. Or if I go back here, what is that? Oh, here is. So at equilibrium, it must be 0. So that is your question number 26. Okay, then. So that was, I guess, Juna. Okay, yes, yes. Okay, okay. Go ahead. 27. Let's see. Prove that the minority carrier distribution is a function of time, considering the combination of carriers only. You can ignore the effect of diffusion in this problem. Okay, so let me check. Okay, that would be 27, 27, 27. So here it is, question number 27, and it should be lecture 4, I guess, the very first one. Yeah. So we are only considering uh, diffusion, right? Oh, sorry, what was the question? I forgot about it. Considering recombination. So there is no straightforward answer for that particular problem in the slide. But let me explain how you can solve this problem. In this particular case, we only consider the diffusion. As a result, uh, because there is no recombination, so total number of particles must be constant. Because we do not have recombination, we do not lose any carrier. So total number of particles must be constant. That's why, and plus we have diffusion. Because of the diffusion, the carrier will spread out. As a result, the maximum carrier concentration will drop, or the height of the carrier concentration will drop, but the base of the carrier concentration will increase, because the area under the curve must be constant without recombination. So now, if we add recombination, what will happen? That was the question. Here we have no, 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 no. So let me explain. So this is our in this particular case we are dealing only with diffusion. There is no recombination. Okay, but if we add recombination, then we will lose carrier, which means this spread will not be that large because we are losing carrier. The spread is increasing, or the width of this distribution is increasing because there is no recombination. That means that we are not going to lose any carrier. But if we lose any carrier, this condition is not true anymore. That means it's not going to spread like this. The peak will drop to zero with time. Does it make sense? Okay. So consider the case with the RC circuit. If we assume there is a resistance in parallel with the capacitor, what will happen if we leave it for a long period of time? The capacitor will discharge through the resistance. So that is, if we consider that as a leakage current, then capacitor will discharge to zero after a particular period of time. So consider recombination as a leakage also. Because we will have leakage, the carrier concentration will die down to zero after a certain period of time. Without recombination, after a certain period of time, the concentration will become constant, a non-zero value. But if we have recombination, then the concentration will become zero after a certain period of time. Does it make sense? Okay. All right. Hopefully that was helpful. Any other question from Zunaid Rafi? Okay. Kaji Salman Ahsan.
No, sir. Nahi.
Okay. Khaled Saifullah.
No, sir.
And another one is Khalid Saifullah.
Yes, sir. Two are
Is
different,
it
sir.
okay? That's better. Khandakar
Sir,
Sajid.
No, sir.
sir, 32 এর তো প্রবলেম ছিল 32 এতে স্যার
Okay, 32. 32. Let's go to 32. Okay, so I think I just explained this one, right?
ইয়েস স্যার
Okay. Any other problem?
নো স্যার
Okay. All right. So I will move on. Okay. Khandakar Sajid.
No, sir.
All right. MD. I don't know how to pronounce Marcy.
No, sir, no problem.
Okay. MD Tanvir.
No, sir.
MD Mash. Sorry. Muhammad Mash.
Yes, sir.
Mash.
I had some questions to ask.
Okay. All right. What is your question?
Sir, for just a second. For number 14 B and C, do we have to just write it down in like a small paragraph, or do we have to show the mathematical calculations?
Okay. Let me see. What is the question? Well, you need to use the Fermi distribution equation because for intrinsic silicon, the probability of finding electron the conduction band is equal to the probability of finding holes in the valence band. If you equate those two probability, you will find that EF is equal to EC plus EV divided by 2.
Okay, sir.
So what you need to do, let me write it down for you. For number A, F AC will be equal to 1 minus F. Now, if you calculate the Fermi level from this equation, then you should be able to get this expression. For number 2,
Yes.
for number B, the expression should be greater. Okay? If you do the calculation, you should get to solve these three equations. If you solve these three equations, you should be able to get these expressions.
Okay, sir. And sir, for number 34 and 35, are these questions in the syllabus? Because we haven't studied Heines-Shockley equations.
Let me check. Number what? Number
For 34 and 35.
34 is included in the syllabus. The only thing is not included, as I mentioned,
It's 35.
35. 35 is not part of the syllabus.
Okay, sir. That's it. Thank you.
All right. So moving on to the next person, Muhammad Fahim.
No, sir.
No question. Muntasir Abdullah.
No, sir, I don't have a question.
Okay. SM Tasin Tahmid.
Sir, can you please explain the 31?
Sure, let me try. 31. Okay. All right. I think I already went through this in the during the class time and also during last tutorial on Friday. Okay, let me try to explain it one more time. So in this particular diagram, we have distribution of carrier concentration. N means electron, P means hole. For both cases, the carrier concentration is higher on the left side than the right side for electron and for holes. And at the same time, we also have an applied electric field, EX, that is going from left to right. Now the question is, we need to find out the particle flow and the current from this figure. So first of all, let's try to calculate all the parameters for holes. There will be two components. One is diffusion and another one is drift. Diffusion will happen because of carrier concentration difference, and drift will happen because of electric field. All right. Now we have more holes on the left side than the right side. So the holes will be diffused from left to right, as shown here. Now next is the I think he already signed in. I mean, joined the meeting. Anyway, what will I say? Now we already discussed about the diffusion. Now let's try to find out the direction of drift, hole drift. For the hole, the electric field is from left to right. If I write down the equation for the hole, the force of equation, F will be equal to, since charge of the hole is positive, so we will use Q and we will use E. This equation says that the holes will flow from in the same direction of electric field. That means left to right. So as shown here, the drift of holes will be also from left to right. The next point is we need to calculate or find the direction of current flow for holes. We know the current flows in the same direction of hole flow. So diffusion hole flows from left to right. That means diffusion current will flow from left to right also. Diffusion drift of holes is from left to right. That means current drift of current of holes will also be from left to right. So we are done with holes. Is it clear for you?
Yes, sir.
Okay. Now let's draw the electrons. First of all, we will check the diffusion. The diffusion is from, the carrier concentration is high on the left, low on the right. So diffusion always happens from high to low. So electron will diffuse from left to right, like this. And for the drift of electron, we know the equation will be Fp and Fn will be minus, there will be minus Qe. Since for electron we have negative sign, the drift of electron will be from will be in the opposite direction of electric field. So electric field is from left to right, opposite direction will be right to left. So these are the two directions of electron flow. Diffusion will be high concentration to low concentration, left to right. Drift will be opposite to electric field, then this right to left. Now we can calculate the current. The diffusion current is for the electron current is always opposite to electron flow. Now the diffusion electron flows from left to right. That means diffusion current will be right to left. I can show you the proof, mathematical proof. Let me go back and do that. Here it is. As you can see, the particle flow is minus dnx by dx. But for current flow, it is plus. Because of minus and minus, it will become plus, which means the electron current flows in the opposite direction of particle flow. So we have it here also. So the electron current will flow opposite direction of electron flow. The current will flow in the opposite direction of the electron. Alright, so since diffusion electron flows from left to right, that means diffusion electron current will be right to left, opposite direction. Diffusion, and we already calculated, drift electron flow will be right to left. So the current will be just opposite direction, left to right. So you have to apply these equations and the convention of current in order to find the exact direction, and all the equations are provided here. So phi represents phi n, phi p is the whole, phi p is for the whole, and these are diffusion. You can also calculate the drift from previous equations also. So these are the equation for the drift, because here we have current flow due to electric potential. Okay, you can see electric field, that means electric voltage also for the potential. Okay, is it clear now? Hopefully.
Yes, sir, I understand.
Okay, good.
Thank you, sir.
Okay, all right, great. Next, who was there? Who was that? I don't remember. Shahriar Alam or oh, no, sorry, Tasin Ahmed, right? All right.
Yes, sir.
Okay. Any other question from Tasin Ahmed? Tasin Tahmid?
No, sir. No, sir.
Okay.
I don't have.
Then next is Shatitho Shah. Any question, Shatitho Shah?
No, sir.
Okay. Syed Shahriar Alam. Any question?
No, sir.
Shadid Al Akib.
Yes, sir. So in the question number 18, we are not given the Fermi energy level for
Okay, let
for
me check.
EF or sorry, EC or EV, and even the temperature is not given. So how are we going to calculate the free hole concentration and free electron concentration?
Check. 18. So your question is, a silicon sample is doped with this and that. All boron atoms and phosphorus are calculate the following. Okay. So you should be able to calculate acceptor concentration, right?
It's the same as the concentration of boron, right?
Of course, right? So I don't see any information missing. You should be able to calculate all the parameters. Okay, if not, then maybe you are not present in the class, or your mind was not present in the class, or maybe something happened. Okay, so you have to read this question very carefully. So we have doping concentration of boron, doping concentration of phosphorus, and the most important thing is all boron atoms and phosphorus atom are ionized. That means the holes from boron atoms and the electrons from phosphorus atom are all available. So acceptor concentration will be exactly same as number of boron atoms. Number of ionized boron atoms. Ionized. This is important. Okay. Acceptor concentration will be equal to number of ionized boron atoms. If I say ionization is only 90%, then acceptor atom would be 0.9 times 10 to the power 14. So similarly, if you want to calculate the donor atoms, then because all the phosphorus atoms are ionized, donor atoms and the donor concentration will be exactly equal to phosphorus atoms, which is 10 to the power 16. Okay. Now, next one is concentration of free holes. Since boron atoms are all ionized, that means it provided all the holes that is available for the boron atoms. All the holes. So when we say all the holes, what is the number for that? How much will be the all? All means 100%. And we have this amount of boron atoms. So and all the boron atoms provided the holes. What will be the hole concentration there?
10 to the power 14 per
10
centimeter
to,
cube.
10 to the power 14, right? Similar to that, all the phosphorus atoms provided the electron, or donated all the electron. So what will be the concentration of free electrons?
10 to the power 10 to the power 16 per centimeter cube.
Yes, 10 to the power 16 centimeter cube. Because it says all means 100%. Now the last question is, you have to write the charge neutrality equation. If you remember, I have that equation here. This is the equation. Acceptor atoms, number of holes, donor atoms, number of electrons. So if I write down this equation here, let's see what will happen. So what was the acceptor concentration?
It was 10 to the power 14 per centimeter cube.
Right. So we have negative sign and acceptor concentration minus 14. And how many holes do we have here?
We have 10 to the power 16 per centimeter cube.
Okay, that's wrong. So where do we get the holes from? Do we get holes from phosphorus or boron?
We get them from boron.
Okay, so how much boron do we have?
Oh, okay. It will be the same as 10 to the power 14. Okay.
So will be equal to number of donor.
Oh,
atoms.
I get it now.
So it will be 10 to the power 16. Okay. How many electrons do we have?
Minus 10 to the power 16.
Right. Minus sign comes from because of the charge,
Yes.
but total number is 10 to the power 16.
Yeah.
So you can see both sides. This will be 0 will be equal to 0. Now we have charge neutral. Okay. All right. Any other question?
No, sir. Thank you, sir.
Okay, that was, I don't remember. Who was that?
Sir
Or
Farid Akib.
Akib. Okay. So next person is Shahriya Siam. My guess.
No, sir, I don't have any question.
Okay. Next one, Shamim Shahed Mahin.
Yes, sir. So can you please help me with 32B?
32B. Okay.
Yes, sir.
B. Okay. Here it is. Determine the built-in field for following distribution. So if you if we go back to our lecture slides, that maybe I don't remember the most of it would be, I guess. It's not here, so all right. So here is the answer, but let me explain it. Okay. So we need to calculate the built-in electric. I think that was the question, right? Built-in electric field for a certain distribution, and that distribution and exactly same as this one. Okay. I think we understand because yeah, you can mute your mic. Okay. So this is our carrier distribution for electrons. We have high concentration on the left, low concentration on the right. We understand the particle diffusion will be from left to right, and corresponding current, diffusion current, will be from right to left, because electron current is opposite to electron flow. And because we do not have any applied potential, so current must be zero, which means that there will be an opposite current. And that opposite current, in order to flow that opposite current, we must have a built-in electric field or electric potential. Okay. So we understand that part. So here is the equation for electron current. One part is for the diffusion that will come from this distribution, and another part is for drift. And we also know, because we do not have any applied electric voltage, so this current must be equal to zero. So if it is zero, so are you following me?
Yes, sir.
Okay. So if this current is equal to zero, the distribution for n is given, so we can calculate dn by dx. And if it is equal to 0, we can cancel out q and q. Now we will have, and because the distribution is given, we also know nx. If it is given, then we must know this thing. So in this equation, everything is given. And also, if you recall, dn by mu n must be kt by q. Where do I have that? D by mu is also equal to kt by q. And in k is Boltzmann constant, T is also a constant because that's room temperature, and Q is also a universal constant. So if I go back to this equation, we see everything is given, or either given or constant, universal constant. So the only thing that we don't know is Ex. So if we replace all these parameters, either given or constant, universal constant, we should be able to calculate Ex. Is it clear now?
Yes, I got it, sir. Thank you so much.
Okay. So just to extend that discussion, I think I have the example for holes in this slide. So let me go through that. Here is the example for holes. if you go back, the equation for holes is this is positive, this is negative, and because we do not have any applied voltage, the current must be 0. So here it is. We have JP. This is due to drift or electric field. This is due to diffusion equal to 0. So if we do the math, you can see we can write Ex is equal to dP by mu P, which we can replace d by mu is equal to kt by q, which are universal constant. Px is given, and we can also, if the px is given, we should be able to calculate px and also dp by dx. So for electron, we will get similar equation, and then therefore because p is given, dp by mu p is universal constant, we should be able to calculate px. Okay. And in the question 32, so that was 32b. 32p is same question, same equation. We have to derive it for electron instead of hole. And our starting equation will be this one. Just like for holes, our starting equation is this one. For electron, our starting equation will be here. All right. Anything else?
No, sir. Thank you so much.
Okay. Okay. So that was Shamim Shahid Mahi, Shushuma Ekela Hussein.
No, sir, I don't have any problem.
Okay. Sayeda Nuzhat Nuri.
No question, sir.
Okay. All right. Okay. We have one more left. Okay. I don't know how to pronounce your name. Do you have any question? I guess it's Usta Gayan. Am I saying it correctly? I hope I'm saying it correctly.
Sir, it's Utsho, sir. I don't have any
Ut-
questions, sir.
Oh, sorry. Utsho. I confuse it SMT. Utsho Gayan. Right. That's better. Obviously. Okay. And you said you don't have any question. All right. I think I covered most of all of you, but anyone has any other question? Okay. All right then. So I think we covered most of the item, but as I mentioned, since we are on the call, I can stay longer if you have any other question. Otherwise, maybe that's it for today. But however, I'm available. I already allocated some time for this session. So I'm still available. If you have any question, let me know. This is not your last chance. You can obviously ask me through the Google Classroom if you have any further questions. But since we are discussing anyway, so why not taking this as take the advantage of this session. Anyone has any other question? Okay. If not, I think we're done for today. And as I mentioned, you can ask me any question through Google Classroom. I will try to answer it as soon as possible. And I don't know, are you going to have any such tutorial with ST? Oh, okay. When it is supposed to be? Tonight? Was it? Okay. I'm going to talk with her, see what is the situation, and if she is not available, most likely I will take the tutorial. Okay. So because you deserve. Um, so let me talk with her first. Then I'm going to announce is there is any tutorial or not. I think she used some other platform, some kind of what are called Discord. Sorry, Discord. Okay. So let me talk with her anyway. So when do you usually have your tutorial with her? Eh, No, no. Weekly tutorial. When is it?
Usually, mostly on Mondays.
Sir, 7:30.
That's the time. What day? Wednesday. Okay. All right. So I think we have few more days. So let's see. Let me talk with her and let's try to understand the situation. Then I will update you in the Google Classroom. Okay. All right. So since until then, go through the questions again. If you have any more question, post it in the Google Classroom, or you can ask me during the. If I am there, if I need to take the tutorial, I can ask me. If she is available, you can ask her also. Whoever is present there. But the best thing is that okay, I'm coming to part one. Best thing is that go through it. Okay, unless you go through it, no matter how many tutorials I take or no matter how many tutorials ST take, it's not gonna be very helpful for you unless you do uh, try to solve those questions first by yourself. Okay, Patwari, what is your question?
So in number 25 of
Where were you?
no sir, it's actually just a question. I'm a bit confused about this, the whole voltage part.
Okay, so question
Number
number
25.
20. 20?
25, sir, 25.
I already discussed that.
No sir, I just want to ask you what is the whole voltage? Is VAB or VCD? That's the question.
What is what? Again, I couldn't understand you.
Sir, what is the whole voltage? Is it VAB or VCD? That's my question.
VAV, whole voltage is VAV.
Thank you, sir.
Okay. So I think there is a confusion about that. So I'm going to update this question because a resistance is missing. So I'm going to do that. So then you should be able to calculate all the parameters. But if you want to solve it before I update the question, assume r equal to 1. Okay. All right. Anyone has any other question? The reason I'm asking, since we are here, let's make the best use of time. So any question, anyone, let me know. All right. Again, um, you may not have any question right now, but if you have any question later at any time, post it in Google Classroom, and I will try to get back to you as soon as possible. And also, I will discuss with ST and see, try to understand the situation, and we'll make our plan according. But either I do it or she does it. There will be another session. All right. If there is no other question, so I think we are done for today. Okay. All right.
Assalamu alaikum, sir.
Wa alaikum salam.